Okay, exercise 4 is another exercise that has a pretty extensive pre-lab that I usually give. So I've split this up into two parts. And unfortunately, for some reason, my title page is superimposed on each other. So that's a little confusing. This is going to be part 1. Okay, so part 1, exercise 4, we're dealing with our microscopy theory here. And part 2, we'll be looking more at the staining aspect. All right, so some terminology I want you to be familiar with. When we get into lab, I'm going to have everybody get out the scopes and we'll kind of look them over. I assume that you have a little bit of familiarity with a microscope, that you've used one a couple times maybe before you've gotten to this lab. But we will look through the parts a little bit, so don't worry about that. Some terms that you need to understand in order to use that microscope most effectively. These are bright field microscopes, light microscopes, right? That's the only kind of scope that we use in this class. And these are, at least in theory, parfocal. And that means when an object is in focus under low power. Remember, there's four objective lenses on these microscope. There's actually the scanning. I often call the 4x low power because it's the lowest, but technically that's the scanning. There's a medium that's 10x, a high that's 40x, and an oil immersion that's 100x. Okay, so when you have your scope in focus under that lowest power, then if we don't change the level of the stage at all and only change the objective lens, okay, that scope should still be in focus. Okay, so that's what parfocal means. When an object is in focus under low power, it will still be in focus when changing to high. Okay, so in theory, these scopes are parfocal. This probably gives students the biggest trouble when they're trying to find their cells. Okay, but this does dictate how we're going to find our cells. We're always going to look for them first under that lowest power, that shortest objective lens. Because if we didn't find them first under low power, if we just, moved the stage up and down when we had it under high power, it's like finding a needle in a haystack. So I've seen people do it. They know sort of exactly where they have to put it, but our best strategy is going to be find our cells first under low power. And it's not going to look like much under low power. Our cells, or our clumps of cells, you couldn't even see a single cell under low power. They're too small. Hopefully you'll see some little dots that are stained a little bit. That's what you're going to want to focus on under low power. Now, a lot of times students like to find it under low, and then they look under medium, and then they look under high, and then they put their drop of oil and look under oil immersion. I wouldn't recommend that. Now, you can switch back and forth between these objectives, definitely, but I would encourage you to find it under low and then put your oil on and go directly to high. The reasoning is that these first 3 lenses are not designed to view cells with the aid of immersion oil. And if you get immersion oil on them, then they get dirty and you can't see them through them right. And they're very difficult to clean out. So once you put oil on there, you can easily switch back and forth between the low and the high, but if you drag this this 40x through the oil, again, it gets all junked up, and we want to avoid that if possible. All right, so I'll harp on you about that when we get to class, but we usually have to fine focus a little bit when we're moving up to a higher power. but it's just a little tweak one way or the other as long as you're focused on the right thing under 4x. Now, sometimes we have to go back and say, well, I'm going to look at this other clump instead of this one and focus that just right. And that's definitely fine, and I would encourage you to do that. But don't be afraid to kind of switch back and forth between those. Okay, obviously we need to have good magnification in order to see our cells. That's the apparent increase in size. And if we wanted to get the total magnification, we would take one of those objective lenses and multiply by the magnification of the ocular lens to get that total magnification. All right, so if we were in our lowest power, our 4x, our ocular lenses, those are the two lenses that you look through with your eyes, those are 10x, so we get total magnification of 40x under that scanning. If we're using our oil immersion lens, then we can boost that up to 1,000 times. Okay, so this is, when I say, in class, hey, find your cells, I always want you to find it under that oil immersion because they really don't look like much unless we kind of bounce it up to that highest power. Okay, now we could get lenses on here that would increase that magnification even higher than this, but above about 1000x, we don't, even if we magnified them, say 2000 times, that wouldn't really give us a better picture, because at about 1000x we start to run into limits imposed by physical properties of light. Okay, so we have to start paying attention to another aspect, and that is the resolution that we're getting. And this is a little bit more difficult to define, but we'll call resolution the ability to see clearly two objects. There as separate, okay, under the microscope. Or you could talk about resolution when you're looking through a telescope or something like that as well. Okay, so I can resolve here that these two dots are separate dots. I can see a space between them. If I were to walk back to the other side of the room, then maybe I wouldn't be able to resolve that difference. Okay, so you can kind of think about resolution as a measure of clarity. It's not the same thing as being in focus. You always assume, my cells are in focus, and then you start thinking about other things like magnification and resolution and contrast. Okay, so on page 17 of your lab manual, there's an equation here that helps us understand how we can improve our resolution. Okay, so the resolving power is equal to the wavelength of light divided by the numerical aperture. I think your textbook has the same equation, and it's got a constant in there. We won't worry about that. The first thing to understand is that resolving power, good resolving power, is a low number. Okay, because this is actually the distance between two dots where we can still tell that they're separate dots. Okay, so if that distance is very small, that's great resolution. If those dots have to be really far apart to tell that they're separate, then that's not so good resolution. Okay, so if we want to get better resolving power, okay, so let's see, to improve resolution, what could we do? Well, we can mess with the wavelength of light, or we can mess with the numerical aperture sort of a little bit. Okay, so if we want this fraction here to get to make this a smaller number, okay, we can either decrease the numerator or increase the denominator. Okay, so mathematically, make sure you understand that that makes sense. If you have a fraction, say 3/4, if you make the numerator smaller, okay, 1/4, that's a smaller number. If you make the denominator larger, yep, that's smaller than 3/4. So just make sure that you kind of understand the math there. All right, so if we could decrease the wavelength of light, okay, let's write that. Decrease the wavelength of light. Okay, so how are we going to do that? Well, that's not easy with light microscopes, right? Visible light is between about 400 and 700 nanometers. Blue light is maybe on the shorter side, maybe closer to 400, 450 nanometers. So we could, in theory, use blue light. And I haven't ever tried that instead of white light, but in theory, that would give us a little bit better resolution. The main reason I bring this up is, what if we use electrons instead of wavelengths of light? Okay, of course, we can't do that with these light microscopes, but if we use electron microscope, that's why they give us such amazing resolution. And we can magnify it a lot higher because we're not limited by resolution. Okay, on the same lines, if we use a fluorescent microscope, we're using UV wavelengths. Say ultraviolet wavelengths are much shorter than visible light, so that gives us a little bit better resolution. Okay, what could we do? What is this numerical aperture? Well, let me go ahead and write this here. Let's see, I got to fit it all on this page. Increase, I'll explain in a minute, the numerical aperture. We could do that by using oil and an oil immersion lens. Okay, so let me illustrate that. Again, this illustration is on page 17 of your lab book. I'm going to write it out again. So say this is your 4x, your low power. I think that has a red line on it. Okay, so this is your lowest power. Here's your slide where you've got your cells on it. Here's your microscope stage, and here's your light source. Okay, so normally when you flip this on and the light comes up through the stage, through the glass, and it hits the air, normally that light bends off on all kinds of angles like this. Okay, that's just the properties of light. Some of it comes up through your objective lens, through your eye, and you can see it, but that's just the way light behaves. If, however, we use our oil immersion lens, I think that has a gray or dark line on it, I forget. And the picture in your book has a cover slip on here for some reason. We don't ever use color slips when we stain cells, so I'm not going to include that. Here's our light source. Remember, with our oil immersion, we're going to be putting a drop of immersion oil right there where our cells are, and this oil immersion lens is designed to touch that oil. If it doesn't come in contact with the oil, it won't come into focus. So you don't want to forget to put a drop of oil on there. So now when the light's coming up through the stage and the glass slide that your cells are on, that oil has the same refractive index as the glass here on the stage and the glass in our objective lens. So it still bends a little bit, but a lot less. So this actually, oil increases the numerical aperture With the numerical aperture, it's sort of the angle of light that gets collected up into the lens. Okay, so it collects a larger angle of light, if that makes sense. A larger span, or collects larger, we'll just say larger amount of light. My physics is weak, we'll say. Okay, so using oil is going to, again, increase that numerical aperture. All right, hopefully then we get better resolution. All right, the last principle I want to talk about is a little bit easier to understand, and that's contrast. That's the ability of cells to stand out from the background. Okay. Obviously, we need to have good contrast. If the cells look just like the background, it's going to be very, very difficult to see them. To improve the contrast, it should be fairly obvious. One thing we can do is to stain the cells. So here, this is a picture from your textbook. Here's some cheek cells that are unstained. And then after they've been stained with maybe one or a couple of dyes. So you can see there's going to be much easier to find under the microscope. Incidentally, these are the nuclei of the cheek cells, and all these little dots that you see around here, those are some bacteria. So that just gives you an understanding of how much smaller bacteria cells are than a typical eukaryotic cell. All right, so that's typically the way that we increase the contrast to see our cells. I'm hoping that we will find a time later in the semester to do a wet mount with our bacteria cells, and that means that we don't stain them. The advantage to not staining them is that we can view them when they're alive. So hopefully we'll be able to see some bacteria cells buzzing around a little bit. So again, staining the cells, unfortunately, this kills them, but we can see them easily. All right. If we are not staining cells and using a regular bright field microscope like we are in class, the other thing that does improve the contrast a little bit is by dimming the light, by adjusting the iris diaphragm. And that's a little lever underneath the stage that I will show you that increases or decreases the amount of light coming up through the stage. Okay, if you decrease the light and you don't stain, then typically that will give us enough contrast that you'll be able to see the cells, but that takes a little bit of practice. Of course, there's kinds of microscopy that are designed to be used where you don't stain the cells, like dark field microscopy or phase contrast microscopy. Hopefully your lecture professor will touch on those and give you an example of what cells look like using those kinds of microscopy, but we won't be using those in lab. Okay, so finally, just a few hints that you ought to have written down somewhere in case you're in lab and you're having trouble finding cells. The good thing is there will only be 10 of you, so it'll be a little bit easier for me to come around and help you. But remember, you're always going to start out under that lowest power. And it's not going to look like very much interesting, but you're going to get that into perfect focus. And then go ahead and add a drop of oil wherever you're looking at your slide and move it up to the oil immersion. Okay, so turn it in such a way, I think it's counterclockwise, so that you don't drag that higher power, longer objective through there. Okay. You will have to adjust the fine focus just a little bit. That's the small knob. Remember the coarse focus, and I will remind you of this in class again, the big knob, you never want to use that coarse focus when you're using your longer objective lenses, because you could scratch them or break your slide. So just going to turn the fine focus just a little bit one way or the other. If you get more than a turn or two, turn back the other way. If you're still having trouble, then you want to go back to low power. Check the diopters. Okay, I will show you where the diopters are in class, but they are at the end of your ocular lenses. Students lean on those and they tend to get out of whack a little bit. If you adjust that back to the center, then it will make your scope more parfocal. Okay, and I'll explain that a little bit better when I can show you, but never be afraid to mess with those a little bit. Put them back on the setting that I'm going to show you, and then hopefully you won't have to focus as much when you move up to high power. Okay, when you put away your scope, you should have this written somewhere. I typically always go around and check and make sure students put their scopes away correctly. We want to make sure we take good care of these scopes. They cost in the neighborhood of $3,000 a piece, so hopefully we can take good care of them. We're always going to move the objective lens back to that 4x, that scanning. So that's the shortest objective. It's the safest position for the scope to be in when you move it. Okay, if you've got one of the longer ones in, if the stage gets bumped, then it could, scratch it or whatever. So we're always going to move it back to that lowest power when you are all done for the day. You're going to make sure that you remove your slide and dispose of it in the little trash can that's right on the benches there. And we will be using that oil immersion every time we have our scopes on, so you're going to clean that oil immersion lens with lens paper that will be in your drawer. Never use anything else other than lens paper. Never use a paper towel, anything like that. Of course, that could scratch it. If you're doing more than one slide, there's no need to clean that oil immersion lens in between. So just wait till you're all done for the day, clean that off, and then you're going to put the scope back in the cabinet. Always use two hands, right? You gotta unplug it and everything, wrap the cord around, put it back in the cabinet with the arm facing out. Okay, so the arm is this part right here. Okay, sometimes students tend to pick it up the other way, and then the next student doesn't have anything to kind of grab a hold of when they get them out. So I will demonstrate that if that wasn't very clear. Okay, so next lecture that I need for you to watch talks specifically about staining and gram staining in particular.